We're going to take a look at the flow rule in this lecture. So remember that blood likes to flow down its pressure gradient from areas of high pressure to low pressure. And to answer these questions, what generates the pressure that drives blood flow? So remember, that's the heart. So the ventricle contracting, that's going to generate that high pressure in the aorta or pulmonary artery, and then that will get the blood flowing. And then the pressure difference between the arteries and the veins. The arteries have much higher pressure because they're right next to the ventricles. And then the veins are much further away from the ventricles, so by the time the blood reaches the veins, the pressure has really dropped. So the arteries have high pressure and the veins have low pressure. So that's why the blood flows from the arteries towards the veins. The flow rule is really important, so you need to make sure that you have this memorized. So all it's just saying is that the blood flow is equal to the pressure gradient difference divided by the resistance to flow. So if we take a look at the pressure gradient difference, the greater the pressure difference, the higher the blood flow. So a good example, this is if you take a Camelback water container and you fill it up with water, you lay it on the table, you unscrew the lid, and if you were just to gently push on the Camelback, just a little bit of water would flow out. But if you pushed really hard, you had a much higher pressure gradient, then a lot more water would come spilling out of the Camelback. The resistance to blood flow, that's an inverse relationship. So the higher the resistance, the less blood you get to flow. And the lower the resistance, the more flow you get. So a good example of resistance would be drinking out of a wide straw versus a narrow straw. So a wide straw would be like the blood vessels being vasodilated. And when you go to drink your water, you would get a lot of flow through the wide straw. But if you're drinking out of the narrow straw, that would be like vasoconstriction. So the blood is going to rub up against the sides more than if you had the wider straw. And so you're going to have more resistance to flow, and so you get less flow through the narrow straw or the vasoconstricted blood vessels. So here's just some pictures just showing you the flow rule. So the top picture is just showing you that we've got a pressure gradient of 40 millimeters of mercury between the top and the bottom of the two containers here where the water levels are. And you can see that we have a flow of 20 mils per minute there. But if our pressure gradient was 0, if there was no difference in pressure between the two sides, notice that the flow would be 0. So this would happen if the heart stopped beating and was no longer generating that pressure gradient. And then this just shows the flow rule looking at the resistance. So on top we've got, in A, we've got the wide straw, or the blood vessels are vasodilated. So there's not a lot of resistance to flow. The blood can flow through, or the water can flow through without rubbing up on the sides very much. And so we get a much higher blood flow there. So we get 20 mils per minute there. But if we have high resistance with the narrow straw or the blood vessels being vasoconstricted, then the blood's going to be rubbing up against the sides more because it's narrower, and we're going to get less blood flow through the vasoconstricted blood vessels. There are 3 factors that affect resistance to blood flow. So make sure you know these. These are really important. So there's the diameter of the blood vessel, the length of the blood vessel, and blood viscosity. The most important of these 3 factors is the diameter of the blood vessel, because the body can very quickly vasodilate and vasoconstrict the blood vessels, and that will affect resistance. But the other 2, the length of the blood vessels and the blood viscosity, those generally don't change, or they change very slowly. So let's take a look at the diameter of the blood vessels first. So I like to think about drinking through a wide straw and a narrow straw. So if you're drinking through the wide straw, that would be like the blood vessels being vasodilated. There's not a lot of resistance to flow because there's lots of room in here, And so the blood or your drink is not going to be revving up against the sides quite as much as if you had a narrow straw. So with the vasodilated blood vessels, we have low resistance. And if you look at the flow rule down here, remember that if you have low resistance, there's an inverse relationship. So if there's low resistance, you have high blood flow. And you know that with your drink, that if you drink through a wide straw, you're going to get more drink through your straw than if you used a narrow straw. So the narrow straw is like the blood vessels being vasoconstricted. And vasoconstricted blood vessels or the narrow straw have a much higher resistance to flow. Because it is narrower, the blood is going to be rubbing up against the sides more, creating more friction, and that'll increase the resistance. So if you look at your flow rule again, if you increase the resistance by vasoconstricting the blood vessels, that will decrease the flow. And we all know that because if you try to drink through a narrow straw, you don't get very much drink through there. The length of the blood vessel is also something that affects the resistance, but it's not something that the body can change very quickly. So I like to think about if you're going to be drinking through a short straw versus a long straw. So the shorter the straw, the less that the blood is going to be rubbing up against the sides because there's a shorter distance to travel, and so the short straw would have less resistance to flow. And so you all know that if you try to take a drink and you're using a short straw, you're going to get more drink through that straw than you would through a longer straw. So the shorter the straw, you're going to have less resistance to flow, and so that would increase the blood flow. And then if you have a longer straw that you're drinking through or longer blood vessels, you're going to have a longer distance to travel, more resistance to flow because the blood will have more chance to rub up against the sides. So the longer straw or longer blood vessels have a higher resistance, and that'll decrease the flow. So where we see the length of the blood vessel being important is if we compare the pulmonary circuit versus the systemic circuit. So the pulmonary circuit would be the short straw because you don't have to travel very far to get from the right ventricle to the lungs. So that would be the short straw. So very little resistance to blood flow in the pulmonary circuit. But the systemic circuit, that's your long straw because you have to go from the left ventricle all the way around your body and then back to the right ventricle. So that would be the long straw, and you'd have much higher resistance to blood flow in the systemic circuit. The last factor that affects resistance to blood flow is blood viscosity. Viscosity is just talking about the thickness of a fluid. So if you think about drinking a milkshake versus water, and let's say that your straw is the same diameter, same length, and if you go to take a drink, you're going to get more drink through the water than you would through the milkshake. So the milkshake has a higher viscosity, it's thicker, there's more friction in the milkshake, so it's not going to flow as much. So the higher the blood viscosity, the higher the resistance, and that would mean there's less flow. And then where we see blood viscosity, dependent on is the concentration of red blood cells and the proteins that are in the blood. So this we don't change very quickly or very often. But if you were living in Nepal at high altitude, for example, you would actually be making more red blood cells because the oxygen levels are lower. And so with a higher concentration of red blood cells in the blood, that would make the blood more viscous. And so it would be more thicker, more resistance, and it would be harder to pump it around, so there'd be less flow. But if you're anemic, where you don't have enough red blood cells, then your blood would be less viscous, and so the resistance would decrease, and that would increase the flow. So we're just going to start changing our flow rule just a little bit. We're going to talk about our total peripheral resistance. So this is just looking at inside the systemic circuit, and we're just looking at the resistance of all the blood vessels within the systemic circuit. So if you vasoconstrict anywhere within the systemic circuit, that'll increase the total peripheral resistance, and that'll decrease the flow. And then if you vasodilate anywhere in the circuit, then that would decrease the total peripheral resistance and increase the blood flow. So we're just going to change our flow rule just a little bit here. So instead of just having the flow equal to the pressure gradient divided by the resistance, we're just going to change that to total peripheral resistance. Okay, let's take a look at the pressure gradient in the systemic circuit. So let's take a look at a picture here. So the pressure gradient we're looking at in the systemic circuit, the highest pressure is in the aorta, which is right next to the left ventricle, which generates the pressure initially. And then the lowest pressure will be in the vena cava right before it goes into the right atrium. So the pressure in the aorta, we're just going to take the mean arterial pressure because remember it's going to fluctuate between the systolic and diastolic pressure. So average mean arterial pressure, the normal there would be around 85 millimeters of mercury. And then by the time the blood gets back to the vena cava before it goes into the right atrium, the pressure in the vena cava is pretty much zero. So the pressure gradient between the aorta and the vena cava, if we subtract those two numbers, the pressure gradient is 85 millimeters of mercury, which is the same thing as the mean arterial pressure. So the pressure gradient for the systemic circuit is the same thing as MAP. So we're just going to change our flow rule again. We're going to call the blood flow cardiac output. So remember the cardiac output is the amount of blood that each ventricle pumps per minute. And then we're just going to change the pressure gradient to the mean arterial pressure, or MAP, and then divide that by our total peripheral resistance. So star this formula. You need to have this memorized. This will definitely be on the exam. Okay, and then if we look at the pulmonary circuit and we look at the pressure gradient there, the pulmonary arterial pressure is 15 millimeters of mercury. And then by the time the blood gets to the pulmonary veins, right before it dumps into the left atrium, then the pressure is down to about zero. So the pressure gradient in the pulmonary circuit is much less than the systemic circuit. It's only about 15 millimeters of mercury. So start with this graph. This is really important to understand. It's just showing you the systemic circuit here in blue, and you can see that the mean arterial pressure coming out of the left ventricle right into the aorta, remember that's up about 85. But then by the time the blood circulates and gets down to the vena cava and right before it enters the right atrium, the pressure goes down to about zero. The pulmonary circuit, the pressure in the pulmonary artery is about 15, and then by the time you get to the pulmonary vein, the pressure will drop down to zero. And the reason that the pressure drops is that the further the blood travels, the more resistance and friction that it runs into, and that will drop the pressure. So what I want you to get from this picture is that the pressure gradient in the systemic circuit is much higher than the pressure gradient in the pulmonary circuit. And that's because of the long straw versus short straw. So let's take a look at that. So let's go over here to the formula. So here's our flow rule up here on top. So we have our blood flow, cardiac output is equal to the mean arterial pressure divided by the total peripheral resistance. And remember, the total peripheral resistance is affected by three things. Vessel diameter, which is the most important because the body can change that very quickly. We also have the vessel length, which is what we're going to look at here, the long straw and the short straw, and then the blood viscosity or thickness of the blood, which is just affected by the number of red blood cells and how much protein is in the blood. So if we take a look at the systemic circuit, okay, remember that's the left ventricle pumping blood out to the rest of the body and then going around, and then it gets delivered back to the right side of the heart. So if we take a look at the flow rule here and we solve for the total peripheral resistance for the systemic circuit, The cardiac output at rest of the left ventricle that serves the systemic circuit is 5 liters per minute. And our mean arterial pressure is 85 millimeters of mercury. And then if we just solve for the total peripheral resistance, you can see that our resistance is 17, so it's pretty high. And then if we compare that to the pulmonary circuit, remember that's the right ventricle pumping blood to the lungs, and then that gets delivered back to the left side of the heart. So the cardiac output for the pulmonary circuit, the right ventricle is also going to be pumping 5 liters of blood per minute. And that's important because remember that the left and right ventricles have to pump the same amount of blood because they're in series, and whatever the right ventricle pumps, the left ventricle has to pump the same in order to keep up. So the cardiac output is going to be the same for both the systemic and the pulmonary circuit. But notice that the mean arterial pressure that's in the pulmonary circuit is only 15 millimeters of mercury. Okay, and the pressure is much smaller because our resistance is much lower. So the resistance in the pulmonary circuit is only 3. So we don't have to generate as much pressure to get the blood around the pulmonary circuit because the blood's the short straw. So the right ventricle doesn't have to be as thick-walled, and it doesn't have to generate as high of a pressure as the left ventricle does in the systemic circuit, because the systemic circuit, that's your long straw. Okay, you've got lots of resistance, your resistance up here about 17. You've got to generate a much higher pressure, much higher mean arterial pressure, in order to get the blood around that very long distance in that long straw, the systemic circuit.